In this video, I will show you how to use the p-series or the integral test to show if an infinite series converges or not. We will do 8 examples. Here's the first one. This is what we have, and let's first go ahead and put this into a sigma notation form. So we are looking at the series as n goes from 1 to infinity. We see that we all have 1 on the numerator, and then this one is 2 square root of 2. This one is 3 square root of 3. The first one is technically 1 square root of 1, and so on. So when we have n, it's just n square root of n. Now, for the square root, we can rewrite that as the 1/2 power. So this is the series, n goes from 1 to infinity, 1 over, this is n to the first power times n to the 1/2 power. Therefore, we can just add the powers. So we get the series as n goes from 1 to infinity, 1 over n, 1 plus 1/2 is 3 over 2. So this is in fact a p-series. We can just go ahead and indicate the p, which is 3 over 2. And because this p is greater than 1, therefore we can say this series converges. And this is by the p-series test. Now, for number 2, again, let's put this in the sigma notation form. So here we have the series as n goes from 1 to infinity. Everything is 1 on the top, and everything has a square on the bottom, right? But now 3, 5, 7, 9, and so on. They are arithmetic, and each time they go up by 2. So the 2 is the coefficient of the n. And when n is equal to 1, 2 times 1 is 2. We need to add 1 more in order to get to 3 for the first term, right? And then square that. So that's the formula for it. For this one though, if you imagine we have 1 over 2x plus 1 and then square, can we integrate that? Yes. So let's go ahead and do the integral test. And to do so, we are going to consider our function to be 1 over 2x plus 1 squared. And before we use the integral test, we have to make sure 3 things for this function. They are, the function has to be continuous, decreasing, and positive. And for my class, I just let my students use a calculator to graph the function, right? That's just some small check, and I'll show you. If you graph this function, this part is going to be something like this. And you can clearly see when x is 1 and later, f is for sure continuous, and it's positive because it's above the x-axis. And lastly, decreasing. So this gives us the right to use the integral test. And for the integral test, we are just going to check the integral going from 1 to infinity of this function. And the integral test says if this improper integral converges, then this infinite series also converges. If this right here diverges, then that right there also diverges. So we just have to compute it. Let's go ahead and do a u sub. Let u equal to the inside. So we have 2x plus 1. Take the derivative, and then divide the 2 on both sides. And we can finish everything in the u world. This right here is x equals 1 to infinity. So in the u world, we put 1 in here. 2 times 1 is 2, and then plus 1 is 3. So u starts as 3. Then when we put infinity to here, 2 times infinity is infinity, plus 1 is still infinity. So u goes to infinity here. And then we have 1 over u squared, and the dx is du over 2. Now for this, we have 1/2, it's a constant multiple. We can put that in the front of the integration. And then write 1 over u squared as u to the negative 2. so that we can use the reverse power rule. Add 1 to the power and then divide it by the new power. So we are looking at 1/2 times -1, so it's -1/2, and then we have u to the -1, which is the same as 1 over u, and then we are going to be plugging the numbers, putting infinity first, so -1 over 2u, and u is infinity, then minus plugging 3, so -1 over 2 times 3. Now this is -1 over infinity, which is just 0. Negative times negative is positive, and then 1 over 2 times 3, 6. So as you can see, this is 0 plus 6, which is, so 0 plus 1 over 6, which is 1 over 6. So this improper integral converges. That means we can come back here and say this infinite series also converges. Why? By the integral test. That's it. Now number 3, series of 1 over n squared times sine of 1 over n. Well, if we look at all the n's as x's, 1 over x squared times sine of 1 over x, can we integrate that? Yes, because the derivative of 1 over x is -1 over x squared, and we have the 1 over x squared at the front that can cancel. So integral test is the way to go, and I will start off by saying let our function be equal to 1 over x squared times sine of 1 over x. And just like earlier, let's go ahead and provide a graph. This time though, if you graph this function, this portion here is going to be going pretty crazy. It doesn't matter. All it matters is what will happen after 1. And the picture will look something like this. So if you look at from 1 and afterward, it's because of the 1 over x, and x goes to infinity. This just jumps up and down. You have the vertical asymptote, so that's what that portion is. You can check on Wolfram Alpha or GeoGebra. But the important thing is f is what? 3 things that you have to mention. Continuous, and it's positive because it's above the x-axis, and lastly decreasing for x is greater than or equal to 1. So this picture suffices. Now we can use the integral test. We check the integral going from 1 to infinity of 1 over x squared times sine of 1 over x. To do so, let's go ahead and do a u sub. Let u equal to 1 over x. Du will be, write this as x to the -1 and bring the power to the front, and -1, we get negative x to the -2, which is 1 over x squared. Now have a look. Here we have negative, but this is positive. Well, I'm just going to multiply by a negative so that I can produce the du. In the meantime though, let's also multiply by another negative so that we stay with the same value. Negative times negative, we didn't change anything. All right, finish everything in the u world. X is going from 1 to infinity. So when x is 1, put it here. 1 over 1 is 1. So u starts with 1. Then put infinity to here. 1 over infinity, we get 0. The order right here might be a little bit different than usual, because usually the bottom number is smaller. But don't worry. At the end, we'll still get the answer, right? The numerical answer for this integral. Here we have the negative, and then this and that together is our du. And then here we have sine of u. If you are uncomfortable with this number being bigger than that, you can use the negative right here to switch the upper and the lower number, right? That's one of the integral property. But you can just finish this as how it is, that's fine too. Now, what's the integral of sine u in the u world? The answer for that is negative cosine. And we have a negative here. So negative negative gives us positive. So we get cosine of u. Just quick check. The derivative of cosine u is negative sine u. Alright, and then we go from 1 to 0 in this order. And then we plug in 0 and plug in 1. So this right here is cosine of this number first. And then minus cosine of that number. Okay, cosine of 0 is just 1. And cosine of 1 is like cosine of 1 radian is another number. And remember, cosine is in between of negative 1 and 1. So no matter what the actual value of this is, we can be sure that this right here is a finite value. Therefore, we can say this improper integral converges. Therefore, we can say this infinite series also converges. But we cannot say this right here also converges to this value. No, we can only say that this right here is also finite. Also converges, and we use the integral test. Done. Now, number 4, we have the series, and we have inverse tangent of n over 1 plus n squared. Can we integrate inverse tangent of x over 1 plus x squared? Yes, because the derivative of integral. Alright, number 4, we have the series of inverse tangent of n over 1 plus n squared. Now, can we integrate inverse tangent of x over 1 plus x squared? Yes, because the derivative of inverse tangent of x is 1 over 1 plus x squared. So, let's use the integral test. Let f of x be equal to inverse tangent of x over 1 plus x squared. And let's provide a quick graph so that we can be sure we can really use the integral test. The graph will look like this. And then, in fact, after 1, our function is continuous, it's positive, and it's also decreasing. Now we have to just compute the corresponding improper integral, which is going from 1 to infinity, and then we have inverse tangent of x over 1 plus x squared. For this, let's do a u sub, let u equal to inverse tangent of x. Take the derivative, we get 1 over 1 plus x squared, and that is exactly what we need for du. Now, x equals 1 up to infinity. Check this out. When x is 1, if we put it here, u will be what? U will be inverse tangent of 1. So tangent of what angle will give you 1? The answer for that is pi over 4. So this right here, we get pi over 4. So u starts at pi over 4. Now, if x is approaching infinity, if you put it here, then it looks that we have inverse tangent. And again, we're taking a limit as x goes to infinity for inverse tangent. We get pi over 2. And that's a horizontal asymptote. So we go from pi over 4 to pi over 2. Okay, we can see that this right here is our u on the top. And then all this is our du. This is very finite, you can see already, right? And let's just finish it. Integrating u in the u world, we get 1/2 u squared, and then we'll just have to be plugging numbers. This goes in first, so we get 1/2, and then pi over 2 squared. And then plugging that, okay, and the rest is just computation. So let's see, pi squared times 1 and then 2 squared is 4 times 2 is 8, and then minus pi squared, yeah, and then this is 16 times 2 is 32. And then cleaning things up, we can multiply this by 4 and 4. So 4 pi squared minus pi squared, we get 3 pi squared over the denominator, 32. Of course, this right here, it's finite, so this right here converges. That means our infinite series also converges by the integral test. So yeah, we're just doing a lot of improper integrals actually, right? Now, number 6, you know how it is. Let's just consider our function. Let f of x equal to x squared over 2x to the third power plus 1. Yes, we can integrate this nicely. And if we take a look at the graph for this, the graph looks like this, right? And then after 1, in fact, once again, the function is continuous, decreasing, and positive. Truth to be told, I chose nice numbers so that you don't get like increasing part at all. It's always going to be starting decreasing. That's why it's like this. But if you have a function that's like this, yeah, even though you have 1, and then it's like increase a little bit, and ever since that it becomes decreasing, technically it's okay. You just have to make a cut somewhere here. Let's say maybe it's like 3 or so, and then you just consider this integral here from 1 to 3. It's finite for sure, and then you do the integral test from 3 to infinity. But I don't want to get into all the trouble, so let's just work with nice numbers in this kind of case. But when you have a picture, I think it's pretty clear as well. All right, after this, of course, let's just go ahead and check our integral. We go from 1 to infinity. Here we have x squared over 2x to the third power plus 1. To integrate this, we do u sub. Let u equal to the denominator, 2x to the third power plus 1. Differentiating both sides, we get du is equal to 6x to the second power. And this is one thing you can do. You can divide 6x squared on both sides and then do the cancellation, or you can kind of just match it. We have x squared and dx. We need a 6. Why don't we multiply the 6 right here? And then don't forget to divide it by it so that we are still maintain the same value of the integral. Alright, so now you see this is 1 over 6. And when x is equal to 1, you plug into here. You will start at 2 times 1 to the third power is 2, plus 1, we get 3. When you put infinity into x, it's just infinity to the third power is infinity, times 2 is still infinity, plus 1, infinity. This is our du. Let's put it on the side. And then this is our u. Okay, now we have the 1 over 6 in the front. Integrating 1 over u, we get natural log of u. We don't need the absolute value because we are going from positive 3 to positive infinity. So it looks like we have 1 over 6 ln of infinity, and then minus, this is the first part, minus 1 over 6 ln of 3. Now, here's the issue. What's ln of infinity? Ln does not have any horizontal asymptote. Ln of x, when x goes to infinity, you get infinity. And then when you divide it by 6, this is still going to give us infinity. And then minus, this is just a finite number. So of course, we still end up with infinity. Therefore, this improper integral actually diverges. So we come here and say this infinite series also diverges by the integral test. Alright, number 7, series, and then we have 1 over n square root of ln n. If you put u equal to ln x, the derivative for that is 1 over x. So yes, we can integrate that. So here we go. Let's consider the function to be 1 over x times square root of ln x. Have a graph right here real quick. Remember though, ln1 is equal to 0, and when x is equal to 1, you actually will get a vertical asymptote for this function. So the function actually looks like this. This is at 1. That's why I purposely started at 3. So if you look at it from 3 and afterward, yes, this function is once again very nice. Continuous, positive, and decreasing. So now we can just go ahead and check our improper integral, and we go from 3 to infinity, and then we have the function 1 over x square root of ln x. For this one, we do a u sub for letting u equal to ln x. du is equal to 1 over x dx, and that's exactly what we have here. So when x is equal to 3, plug into here, u will go from ln 3. And then when x is equal to infinity, ln of infinity will give us infinity. So u goes to infinity as well. Then we will have 1 over square root of ln x, which is the u. And the 1 over x and the dx together, they give us the du. Now for this, we are just going to integrate ln 3 to infinity. Rewrite 1 over square root of u as u to the negative 1/2 power, so that we can just add 1 to the power and we get 1/2, and then divide it by the new power, which is the same as multiplying by 2 over 1. And then we get 2 u to the 1/2, which is the same as square root of u. And then we are going to be plugging numbers. So plugging infinity first, we get 2 square root of infinity, and then minus plugging ln 3. So 2 square root of ln 3. Now for this, square root of infinity is infinity times 2. We still get infinity. So the first part is infinity. And this right here is still just a finite number. So for sure, the result is infinity, which means we have a divergent improper integral, which implies our infinite series also diverges by integral test. Alright, last question here. We have the series as n goes from 1 to infinity, and then we have n times e to the negative n squared. Yes, if you replace the n's with x's, we can integrate that. So let's go ahead. Let's call our function to be x e to the negative x squared. And then let's just do a quick check for the graph. It will look something like this. And yes, after 1, right, f will be again continuous, decreasing, and positive. So we can legitimately use the integral test now. Alright, let's go ahead and check the integral going from 1 to infinity, x e to the negative x squared. So for integrating this, we put u to be negative x squared, and then du equals negative 2x dx. Now if we want to match it, you see that right here we will need the negative 2. So let's go ahead and multiply by the negative 2. And just have to remember, divide it by that right away. So yes, this and that gives us the du, which is super nice. Now, when x is equal to 1, plugging 1 here, we get negative 1 squared, which is negative 1. And when x is equal to infinity, put it here, we get negative infinity squared. So it's negative infinity. and then we have the negative 1/2 in the front, and then this and that is our du, and then we have e, this part is our u, so e to the u, just like that. In this case, once again, we see that this number is smaller than that, and yes, you can use the negative sign right here to switch this and that, but you don't really have to. So I'm just going to do it like this. I have the negative 1/2 right here. Integrating e to the u, we get e to the u. Now we are going to be plugging this and that. Negative infinity goes in there first. So we get negative 1/2 e to the negative infinity. Then minus, plugging negative 1. Alright, here's the deal. E to the negative infinity is the same as 1 over e to the positive infinity, which is going to be infinity on the bottom, which tells us this thing will be 0. So that's 0 times that. Of course, we get 0. And then this right here is finite. It's just going to be plus 1/2 e to the negative 1, which is the e down here, which is just 1 over 2e. And of course, that's finite, so it converges. Then we can come here and say, this infinite series also diverges. No, just kidding. Also converges by integral test. Okay,